Hello everyone, this is Miss King. In this video, we're going to be talking about the next topic in thermochemistry, which is heat and changes of state. So the most important observation to make for this topic is that heat is released or absorbed during a state change if we're going from solid to liquid, liquid to vapor. Example, ice absorbs heat as it melts, changing from a solid to a liquid. We've all experienced that absorbing heat as we touch ice or snow, and we feel it sucking the heat out of its surroundings, so out of our hand, to facilitate its state change, going from a very orderly solid to a less orderly liquid. Fascinating to me is that the converse is also true, that when liquid water freezes, it's going to release heat as it changes from the less ordered liquid into a more ordered solid. A very cool example of this is that in orange orchards that are susceptible to frost, so if their fruit freezes, it's going to damage the fruit and it's not going to be as valuable. What they'll do if they see in the forecast that there's going to be a hard freeze at night, they're going to spray down their orange orchard with liquid water so that as those cold temperatures come in, and the temperature drops, that water will freeze, and through the process of freezing, it's going to release enough heat to keep those oranges from being damaged. Super clever, very cool application of heat and changes of state. Let's turn our attention next to the heating curve of water. We've seen one of these before. Let's look over at the graph. On the y-axis, we have temperature. On the x-axis, we have heat supplied. And it's showing us the state and the temperature of water as heat is being added. So let's read this graph as a story from left to right. So down here we have a very cold solid. Since this is water, we can call that ice. As we're heating up that ice, more heat, the more the temperature is going to rise until you hit the melting point. So for water, this is 0 degrees Celsius. At the melting point, instead of that heat increasing the temperature of the substance, it's going to go towards a state change, going from the more ordered solid into the less ordered liquid. So we can see that there's a change in enthalpy here. Let's look over to our left to learn more about that. So that delta H fuse, that's called the molar heat of fusion. And that's the amount of energy or enthalpy required to take 1 mole of a substance from a solid into a liquid. The converse also occurs when you go from a liquid to a solid. Same amount of energy, but opposite sign. So this actually releases heat, like that example with the oranges. And we call this the molar heat of solidification, since it is going into the solid form. Awesome. So that's first state change. Then liquid, once it's all liquid, we can add heat again, increase the temperature until we hit the boiling point, where when we add more heat, it doesn't increase the temperature, it goes towards a state change. This is a big reservoir of energy right here. And let's see, what is that called? What is that change in enthalpy? That is called your molar heat of vaporization. And that's the amount of enthalpy or energy that needs to be added to change a mole of a substance from a liquid into a vapor. The converse can also occur. You can take a mole of vapor and turn it into a liquid. And we call that the molar heat of condensation. And again, very interesting for water. That's a lot of energy that can go in before creating that less orderly gas. It'll probably come as no surprise to you that different substances take different amounts of heat to go through their state changes. You might have to reference a table like this that shows those different substances and includes heat of fusion and heat of vaporization. So remember, heat of fusion, that's going from a solid to a liquid. If I had a problem where I was solving for the amount of energy that it takes to go from a liquid to a solid, which is your heat of solidification, I just need to look up this value and use that number, but a pen to add a negative sign to the front, since it's the same amount of energy required It's just instead of putting the energy in, that energy will be released in the opposite state change if you're going in the other direction. One more thing, it's a kind of a related topic, doesn't fit in perfectly, but we're going to look at heat of solution. So we spent all last unit talking about these solutions where we have a solute dissolved into a solvent. And it turns out during the formation of a solution, heat is either released or absorbed. Problems related to heat of solution will focus on this value, the molar heat of solution, delta H solution. You can see that written right here. That's the enthalpy change caused by the dissolution of 1 mole of a substance. So how much energy is either released or absorbed by dissolving 1 mole of a solute. Here are 2 cool examples that show that these heats of solution can either be positive or negative. In this example, we have an exothermic reaction, so a hot pack, if you've ever had one of these. An instant hot pack is like a big sealed white bag. You can see a picture of it here. And there'll be a salt at the bottom of it. You can kind of feel the crystals if you had one in your hand. And inside of it, there's a second little baggie that's filled with a liquid. That liquid is just plain water. And the way you start the hot pack is by grabbing it and squeezing hard enough that you pop that baggie on the inside and release the water so that it can go and dissolve your salt, and this reaction will occur. So in these instant hot packs, they often mix calcium chloride with liquid water, and that heat of solution is negative and produces an exothermic reaction if you want to take a look at that thermochemical equation. The opposite is also possible with different salts. We have instant cold packs that use an endothermic heat of solution. So in this example, we'd have solid ammonium nitrate crystals that are going to combine with liquid water, dissolve, and that process absorbs heat. We have a positive delta H solution, a positive molar heat of solution. So those are all of our new concepts. Let's finish off with a little bit of practice. So here's our first practice calculation. It asks how much heat is absorbed when 63.7 grams of water at 100 degrees Celsius and 101.3 kilopascals is converted to steam at 100 degrees Celsius. Express your answer in kilojoules. I'm going to point out a couple of things to you. The first one is this pressure is just telling us is at standard pressure, so we don't actually have to worry about that value. And then the other one is that we're going from water, liquid water at 100 degrees Celsius, to steam, water vapor at 100 degrees Celsius. There's no change in temperature, so all we have to worry about is the energy involved in the state change. Go ahead, pause this video now, and work through this problem on your own. Now that you got a chance to do that calculation on your own, I'll show you how I approached it. I took the value of the mass of water that was given to us in the problem, and I used that as the value that I was starting with. As you can see, looking at the work, we're going to approach this like a stoichiometry problem, where we start with a given, and through using conversion factors, we're going to arrive at our desired value. In this case, I'm going to be converting for the heat that's absorbed during this state change. First thing I do is I use molar mass to convert from grams of water to moles of water. And the next step, this is what's new to us, is using the molar heat of vaporization of water, which I found in this table here, molar heat of vaporization of water, to get my other conversion factor, that when I do the multiplication, when I do the math, is going to give me 144 kilojoules of heat absorbed in this state change. Let's do one more calculation for practice. I want you to calculate this time how many kilojoules of heat are required to melt a 10.0 gram popsicle at 0 degrees Celsius. Assume the popsicle has the same molar mass and heat of fusion as water. Go ahead and pause the video here so you can look at this table while you're doing your calculation. So nice work, everyone. This is our last topic of the unit. We're closing out on the summary slide of heat and changes of state. Tomorrow and on Friday, we're going to be doing practice problems to kind of wrap up that unit, so please reach out if you have any questions. And on Monday, we're going to be having a quiz, and we'll be sending more information about that to you. So just like any other time, let us know if we can help in any way, and have a lovely day.